We had Star Trek in our first talk. Now we go to robots in our third talk with J.P. Hushman from Los Angeles.
Thank you. I would like to thank Mark and the committee for their very kind invitation. My disclosure relevant to the talks are several patents filed through UCLA and some grant supports, mostly from the NIH. Robotic surgery really started in 2000 when the Da Vinci surgical system became FDA approved for laparoscopic surgery. Since then, the number of surgical procedures which benefit from this technology and the number of robotic systems installed worldwide has been increasing steadily. Interestingly, the ratio between traditional versus robotic surgery for those surgical procedures addressed with robotic assistance is evolving quickly. In the US, for instance, almost all prostatectomy are performed with robotic assistant currently. Compared to traditional surgery, robotic surgery provides some superhuman dexterity and improved visual feedback. As we all know, the human body presents some limited performances, and during traditional eye surgery, we'll still rely on limited feedback, limited spatial resolution and depth perception, but also almost no tactile feedback as it is below the threshold for human perception. Also, dexterity and physiologic end tremor make some very delicate manipulation challenging. So robotic assistance can really improve our performances, filtering the tremor, scaling the motion. Collaborative capabilities can augment our manipulation capabilities, while a better feedback through augmented visual feedback and enhanced tactile feedback can lead to better surgical outcomes and also open the door for new surgical manipulations. So robotic system offers different level of collaborations, from the traditional surgery where the surgeon is manipulating and controlling all the surgical tools, to semi-autonomous system where surgeon and robot control simultaneously the intraocular tools, to fully automated system when the robot will fully control all the surgical tools while the surgeon will oversee the surgery and overriding if needed. For retinal surgery, we envision a system with semi-autonomous capabilities. Different designs are proposed, from the end-all smart tool, where all the technology will be incorporated in the end-all, such as the tremor canceling system, to co-manipulation system, where a dedicated tool will be controlled simultaneously by the robotic manipulator and the surgical hand, to telemanipulation, where the robotic manipulator will be controlled from the robotic controller, potentially located at the surgical cockpit. So a couple of systems have been tested so far on humans successfully. One is the system designed by the University of Leuven in Belgium, which is based on the co-manipulation design and successfully tested for retinal vein cannulation. As you can see here, the dedicated instrument is controlled simultaneously by the robotic manipulator and the surgeon's hand. The other system is the Precise, which was designed by Marc de Smet and based on the telemanipulation design, where the instrument is mounted on the robotic arm, controlled from the robotic manipulators by the surgeon's hand. This system has been recently CE marked and approved in Europe and currently used in 3 different hospitals. Our system at UCLA is based as well on the telemanipulation design. It's currently funded by 2 R1 grants. And compared to the other system which are providing to the surgeon the only visual feedback provided by the surgical microscope, we have integrated an OCT which do real-time acquisition and real-time data processing, allowing for enhanced visual feedback, but also haptic feedback through the surgical controllers. This system also allows for semi-automated or automated tasks using the OCT guidance to define some trajectory, safe trajectory within the working space. Our system has been successfully tested for cataract surgery as a fully automated fashion on harvested pig eye, and we hope that our platform will be ready for clinical trial in 3 years. For retinal surgery, we are envisioning a system with semi-autonomous capabilities where the surgeon will be seated at the surgical cockpit and immersed with augmented sensory feedback, visual feedback through the real-time image processing, and as well tactile feedback through the robotic controllers. We demonstrated recently that the addition of tactile feedback in addition to the visual feedback was allowing for faster learning curve and safer tissue manipulation. We hope that our platform will be ready for human trial in 2024. In summary, robotic surgery is still in its infancy in ophthalmology, but we really think that this technology has the ability to provide superhuman capabilities and improve our surgical outcomes and potentially open the door for new tissue manipulation. I would like to thank my collaborators from UCLA. Thank you very much.
Thank you, Jean-Pierre.